Welcome back. In our last lesson, we learned the general concept of a neural network, inspired by the brain. Now, we're going to travel back in time to meet its very first ancestor, the perceptron, the simplest possible form of a neural network. Invented way back in 1958 by a psychologist named Frank Rosenblatt, the perceptron was a groundbreaking creation. It was the first algorithm that could learn and adapt from data, establishing the foundational concepts that are still used today. It is, without exaggeration, the hello world of neural networks. While simple by today's standards, understanding the perceptron is crucial for understanding its much more powerful descendants. The basic structure of a perceptron should look very familiar to you. It's built on the exact principles we discussed in the last lesson. It takes a set of inputs. Originally, these were just binary zeros and ones. Each input is connected to the neuron with a corresponding weight. The perceptron calculates the weighted sum of these inputs and then adds a bias. This core mechanism of aggregating weighted evidence has remained unchanged in even the most advanced neural networks of today. The first major difference between a classic perceptron and a modern neuron lies in its activation function. The perceptron uses what's called a Heaviside step function. This sounds complex, but it's incredibly simple. It's a hard binary threshold. If the weighted sum plus the bias is greater than 0, the neuron fires and outputs a 1. If the sum is 0 or less, it doesn't fire and outputs a 0. There's no middle ground, no probability, just a clear yes or no decision. The learning algorithm for the perceptron is also beautifully intuitive. It processes one training example at a time. It takes the inputs, makes a prediction, and then compares that prediction to the correct answer. If the prediction is right, it does nothing. But if it's wrong, it makes a small adjustment to its weights. If it wrongly predicted a 0 when it should have been a 1, it nudges the weights up slightly. If it wrongly predicted a 1, it nudges them down. By repeating this simple, predict and correct, cycle over and over, the perceptron slowly converges on a set of weights that solves the problem. However, this elegant simplicity came with a massive limitation, one that would famously stall AI research for years. The perceptron can only learn to solve problems that are linearly separable. This means it can only find a solution if the different classes of data can be separated by a single straight line. While it can learn simple logical functions like AND and OR, it is completely incapable of solving the classic XOR problem, because there's no single line that can correctly divide the XOR data points. This failure on the XOR problem was a historic moment, but it led directly to the next great breakthrough. It proved that while a single neuron is limited, the real power might lie in combining them. By connecting perceptrons together in layers, we can overcome the limitation of linear separability and create complex, nonlinear decision boundaries capable of solving fantastically difficult problems. You now understand the fundamental building block. In our next lesson, we will see how we assemble these blocks into the powerful structures we know as modern neural networks.